Hello, in this video we study concavity and second derivative test. In mathematics, we have different ways to define concavity or convexity. But in this video we use the second derivative to determine convexity and concavity. Okay, look at this. If you look at this picture, we have very naive definitions, right? So the function or the graph of a function is called convex or concave upward. If the graph looks like this, okay, and the graph is concave or concave down. If the graph looks like this, I only use convex and concave, right? So but sometimes in the textbook they use concave upward or concave down. So two examples of such functions is, first one is x squared, y equal to x squared, right? That is parabola, and you remember the graph of x squared looks like this. Right? So it's obvious that the graph is convex. Is that correct? Convex. So you might choose another one. Let's say y equal to negative x squared. Okay, so one is x squared, another one is y equal to negative x squared. So you have the following picture. So this graph is concave or concave down. All right. So you might think, if a function is convex, then the negative of that function is concave. Is that correct? Because when you apply y equal to negative f of x, so basically you just flip the graph, right? And then from convexity you get concavity. Okay. Now let's look at convexity and concavity from the point of view of the first derivative, and we will give a definition based on that. Suppose that you have this graph, and suppose that the function is differentiable. Okay, that means the graph of this function has a tangent line everywhere. Okay, so let's say that is y equal to f of x, and f of x is differentiable. That means the graph has tangent line at any point, okay, on the considered interval. All right, now, and we suppose that the graph looks like this. So let's analyze tangent line. Okay, let's say we are here. Look at this, and each time, let's say this is the x-axis. Okay, so this is the alpha, and the slope of the tangent line is equal to tangent of alpha. We know that. Since the graph is convex, right? So if you move this along on the graph, you might see that the angle alpha, if alpha is a function, then the angle alpha is increasing, right? The angle alpha is increasing. So I say tangent alpha is increasing, right? Tangent alpha is increasing, but what is tangent alpha? Tangent alpha in that case, that is the slope, you see? So that is the derivative, is increasing. You see that? Look at this. If you look at this, right, you just move, and then tangent equal to 0 in here when when you have minimum in here, right? And then if you move to this direction, again the alpha also increase. You see this? So basically the derivative is increasing if the graph is convex. Is that correct? So if you doubt about this, right? Let me draw the unit circle and we talk about the angle, okay? So if you have unit circle in here, here's the tangent A6. Okay, so look at this. From this point, you have this alpha, and then alpha is increasing, right? Alpha is increasing, but in this case, alpha is bigger than pi over 2. Bigger than pi over 2. That means alpha is around here, right? When alpha is increasing, you see, here's the tangent, right? And when alpha move to this increase, right, to this guy, so you see the tangent value also increase. You see that? But in this case, the slope is negative because this is 0. This is negative, this is positive. So when alpha increase to pi is this case. You see? Pi is this case. So you have, this value just increase to 0. So just change from negative to 0 and then change the sign. You see? When you're moving to this direction, your alpha is in the first quadrant. So your alpha is right here, you see? And then your tangent is positive. So that's why, if the graph is convex, then the tangent of that alpha is increasing from negative infinity to 0 and then to positive infinity. Is that correct? I mean, in the direction from negative to 0 and to positive. So that's why the convexity is equivalent to the condition that the first derivative is increasing. Does that make sense? Or what does it mean? The first derivative is increasing. We know from the previous section, the first derivative is increasing if x derivative is positive. Does that make sense? So if you look at the first derivative as a function, then the derivative of that function is positive. That means, the derivative of the first derivative is positive. But what is the first derivative of the first derivative? That is the second derivative. So, convexity is equivalent to that, y prime is increasing. And that is also equivalent to the case when y2 prime means the second derivative is positive. Alright, so you have this. Similarly, you might talk about concavity. Okay, similarly we can talk about concavity, but that is very simple picture. Because as we mentioned previously, a function is concave if the function negative f of x is convex. Is that correct? So you apply exactly what you have in here for the function negative f of x. Does that make sense? In that case, f derivative is increasing and negative to f prime is increasing. That means I write here f derivative is decreasing, right? And this guy negative f prime is increasing, means negative 2 prime is negative. So the negative of f2 prime is negative, means f2 prime is positive. Because we have positive out there, right? It's positive. So we have this is negative. In general, a function f is concave if the first derivative is decreasing or that is equivalent to the case that, to the condition that the second derivative is negative. So that's what you have, how to use the first derivative and the second derivative to test if a function is convex or concave. Does that make sense? So similar to the previous problem when we need to find the intervals where the function is increasing or decreasing, we might find intervals where the function is convex or concave. All right. And of course, when you consider a function, you might have points where the function change the convexity, right, and concavity. That means when the function changes from convex to concave, so such points are called inflection point, right? So similar to the case of the first derivative, when we analyze the sign of the second derivative, we need to find all points where the second derivative is equal to 0 or the second derivative does not exist. Such points are called inflection point. Okay. So if you remember the case, right, when we use the first derivative to find local extrema, so we have critical points, right? Those are points where the first derivative equal to 0 or the first derivative does not exist. Remember that? So this is almost the same thing for inflection points, right? We still need to find all points where the first derivative equal to 0 or the first derivative does not exist. So in order to find intervals where the function is convex or concave, right, we need to solve the following steps. So the first one, I need to find, second derivative. The second one, I need to find all inflection point, right? And then the last one is make a chart for second derivative. So if you remember how we did that, for local extrema, so now we just do for second derivative instead of the first derivative, right? We need to determine the open intervals on which the graph of the function f of x equal to 1 over x squared plus 3 is convex or concave. So we need to work with the second derivative. Okay, we need to work with the second derivative. Let's find second derivative. So first I need to find the first derivative. I can rewrite this as x squared plus 3 to -1, and then I differentiate that. I use the chain rule, so I have negative x squared plus 3 to -2, right, times the derivative of inside a function. So I have, okay, let's say negative 2x, x squared plus 3, -2. Right? That is the first derivative. They ask us about convexity, concavity, so you don't need to find critical points. Okay? Now let's find the second derivative of this function. And we need to use the product rule because I have product in here. The -2 is just coefficient. I take that out. Derivative of x is just 1, so the first term is x squared plus 3 to -2. The second term I have plus x. Then I use the chain rule to differentiate this part. I have -2 times x squared plus 3 to negative 3, and then times 2x. Now we need to simplify this, and we did this, I think, several times, and now I will take this term out, because if you compare power, you have negative 2 and negative 3 in here, right? So I will take that out. I have negative 2 x squared plus 3 to negative 3. Inside, from this term, I will get x squared plus 3 to the 1, because when we take negative 3 out, the power in here should be negative 2 minus negative 3. And here I have negative 2 is 4x squared. Does that make sense? So I can rewrite as follows: negative 2, okay, I have x squared plus 3 to 3. And then here I have x squared plus 3 minus 4x squared. I simplify this, I get negative 2, and then negative 3x squared plus 3 over x squared plus 3 cubed. I will take negative 3 out, so I get 6 in here, and then x squared minus 1 over x squared plus 3 cubed. So my second derivative looks really good, right? Not bad at all. And then in order to see the sign of the second derivative, we need to find all inflection points. So I need to set the second derivative equal to 0. Okay, so in this case I have x squared minus 1 equal to 0, or x squared equal to 1. Then I have x equal to plus minus 1. Perfect. Everything with this is okay, because like critical points, right? Sometimes we need to find points where the first derivative does not exist, and then for the second derivative we also need to do almost the same thing. Does that make sense? But x squared plus 3 is defined everywhere, so we are good. Actually, yeah, 1 over x squared plus 3 defines everywhere. Okay, now I will make a chart for the second derivative. I make the chart line for the first derivative. So we have 3 rows in here. The first row is x, the second row is y2 prime, and the last row is y. The function is defined everywhere from negative infinity to positive infinity. We have negative 1 and 1 in here. At 1 and negative 1, the second derivative is 0. So basically I have 3 intervals, right? Now I pick 1 point from each interval. For example, here I pick 2. I plug 2 into the second derivative. I see, yeah, in this case we have positive, right? And then from here I can pick 0. I plug 0 in into the second derivative. I get negative. In here I can pick negative 2. Okay, I plug negative 2 into that. I get positive. So on this interval, the function is convex. On the second interval from negative 1 to 1, the function is concave, because the second derivative is negative. And in the third interval, the function is convex. So I have the following, feeling, right? Convex, I write like this. Concave, I write like this. And convex, I write like this. This helps me to determine the behavior of the graph on such interval. Does that make sense? So if you want to graph that, sometimes we use this information. Not sometimes, or most of the time, if you want to graph the function. Does that make sense? So I may do the conclusion. The function is convex on negative infinity to negative 1 union with 1 infinity, and concave on negative 1 to 1. In this case, the graph has 2 inflection points, negative 1 and 1, where the graph changed the convexity. You see, the function is convex on negative infinity, and then at negative 1 the function changed the concavity. You see this? So you might think about, the graph look like this. And then at 1, the function change convexity again. Okay? Let's consider one more example before we move to the second derivative test. We have function x squared plus 1 over x squared minus 4, and they ask us to determine the open intervals where the function is convex or concave. So we need to find the first derivative and then find the second derivative, and we'll see how the second derivative change the sign. Okay, so the first derivative is equal to 2x x squared minus 4 minus x squared plus 1 times 2x. We use the quotient rule, right? Here we have x squared minus 4 squared, and we simplify this, we get 2x cubed minus 8x minus 2x cubed minus 2x over x squared minus 4 squared, and then that is negative 10x over x squared minus 4 squared. Now let's differentiate this function to get the second derivative. Okay, so I have y prime, y2 prime is negative 10, right? Again, I will use the quotient rule. Derivative of x is 1, so I have x squared minus 4 squared minus x times derivative of x squared minus 4 squared. That is 2x squared minus 4 times 2x. Alright, we use the chain rule for that term. And here divide by x squared minus 4 squared. No, to the 4. And since you have x squared minus 4, x squared minus 4, and x squared minus 4, you might simplify. You have negative 10. Here we have x squared minus 4 cubed, right? On the top, I have x squared minus 4 because we already simplify 1. In the second term, I have minus 4x squared. So I have negative 10, negative 3, x squared minus 4, right? Divided by x squared minus 4 cubed. Or you may rewrite this as 10, 3x squared plus 4 over x squared minus 4 squared. We need to find all inflection points, right? Where the second derivative equal to 0 or the second derivative does not exist. Again, right? Okay, you set this equal to 0, so that is basically the top equal to 0, 3x squared plus 4 equal to 0. You don't have any solution in this case because 3x squared is positive, right? And 4 is positive, so the right hand side part is always positive. No solution for the case to y2 prime equal to 0. And we see y2 prime, the second derivative, does not exist at x squared minus 4 equal to 0. But again, these points are not in the domain of the function, so they are not inflection points. Okay, but we still need to determine them, right? So you have x squared equal to 4 and then x equal to plus minus 2. At these 2 points, the function is not defined and the second derivative is not defined. I think I do something wrong here. So here should be 3, right? Not 2. Okay, now given that the function does not have any inflection point, we still need to consider the sign of the second derivative. Does that make sense? So we have plus minus 2 in here. Plus minus 2, you see that. What are they, right? So I make a chart, x in here, y2 prime in here and then y here. The function is defined everywhere except 2 points. You see, this is the function, and the domain of the function is the whole number line except 2 points, plus minus 2. Is that correct? So, in the first row, we have plus minus infinity and plus and minus 2, negative 2 in here, and then plus 2 in here. And we know at these 2 points, the function and the second derivative, are not defined. So I write, 2 vertical lines in here. That means, pole, the first and the function are not defined. Agree? And then we have 3 intervals. So you pick one point from here, for example, 3. In here you might pick 0, and in here you might pick negative 3. You plug, 3, 0, and negative 3 into the second derivative. But the top is always positive, so you only care about, x squared minus 4 cubed. When x equal to 0, you have negative 4 cubed, that is negative. When x equal to 3, you have 9 minus 4 cubed, which is positive. In here, you also have positive. So in this case, in this interval from negative infinity to negative 2, the function is convex. In here, from negative 2 to 2, the function is concave. And in 2 infinity, the function is convex. So, I used to write this convex, concave, and convex. Agree? So, that's it. And look at this. Right now, we don't say anything about graphing the function, right? About the graphing the function. But, using this table, you would think about, yes, actually, the graph of the function should have 3 parts. The first part is corresponding to the first interval, negative infinity to negative 2. Why? Because, the function is not continuous, right? At negative 2 and 2. You see this? The function is not defined at these 2 points. So, if you have graph, here's the x or y plane, and suppose this is negative 2, that is 2, right? So you have 2 straight line. You see? And based on this picture, based on this chart, you can see, we have 3 branches. I don't know exactly what happened in this area, but I know the graph should look like this. Maybe the graph should convex, right? Or maybe like this, or maybe, something like this. But, that is our hope, right? That is our guess. And, if we want the exact graph of the function, we need to graph them. But we'll do that in the next sections. Okay. When x between negative 2 and 2, so you should have something like this. Is that correct? And another one, you might have something like this, or, something like this. But your graph should be convex in this part. Agree? So, we understand, right? Using the first and the second derivative, we may understand the behavior of the graph of the function. Agree? Now, let's move to the second derivative test. Remember that we use the first derivative test to see if an axioma, a relative axioma, is minimum or maximum. Let me remind you about that. So we did the following chart: x, first derivative, and the function. For example, you have 2 critical points, right? Let's say x1 and x2, right? So here you have derivative equal to 0. And suppose you have plus in here, minus in here, and plus in here. Okay, this is just, an example. So the function is increasing, decreasing in here, and then increasing in here. The first derivative test says if the first derivative change from positive to negative, your axioma should be maximum. And if the first derivative change from negative to positive, your extrema should be minimum. I mean, at that point, right? Does that make sense? And now, we use the second derivative test to classify local extrema. Right? How? Look at this. If your graph is convex, okay, and suppose you have some, that is your x1, fx1. So this is critical point. Then, if you are in this picture, right, in this situation, you see the second derivative at x1 should be positive. Why? Because the graph of this function is convex. Is that correct? Convex means the second derivative on that interval is positive. And of course, at x1 should be positive. In that situation, x1 f x1 is local minimum. Does that make sense? So, in case, if you have this picture and at this point, for example, x1, fx1, and your second derivative at x1 is 0. You see this? So this point is inflection point, right? So you don't have extrema at this one, because at this point the function just changed convexity, right, from convex to concave or from concave to convex. So in this case, no extrema. Is it correct? You still have one more case when x1 fx1 in here, right, and your graph look like this, concave. And it says, in this case, if your second derivative at x1 is less than 0, then x1 fx1 is local maximum, because the function is concave. There's no way to be minimum. Is that correct? So that's how we can use, second derivative test. Alright, so based on this picture, in order to use second derivative test, you need to find all critical points. Right? You need to find all critical points. Second one, you need to find the second derivative. And then the last step is, you plug all critical points into the second derivative. Okay, if the second derivative at x0 is less than 0, that is your maximum. Okay, this is relative maximum. I write local maximum in here. If the second derivative at x0 is greater than 0, that is local minimum. And if the second derivative at x0 is 0, no extrema. Okay, so please just follow the instruction. All right, let's consider the following example, and you will see sometimes we use second derivative test and it is faster than the first derivative test. You have function y equal to negative 3x fifth plus 5x cubed. Okay, we need to find all relative extrema. So I need to find, all critical points, right? As we have seen here, 5 critical points. So I need to take the first derivative, that is negative 15x to the fourth plus 15x squared. I set this equal to 0 because the derivative is defined everywhere. We have only one case, the derivative equal to 0. So I factor 15x squared out. I get negative x squared plus 1 equal to 0. Then from here I get x equal to 0 or negative x squared plus 1 equal to 0. So we are good with 0. for the second one, I get x squared equal to 1 or x equal to plus minus 1. So you see we have 3 critical points, right? Which is good. Now we don't need to consider the side, right? Now I will differentiate one more time to get the second derivative. And that is 60 x cubed plus 30x. And I set this equal to 0. Oh no, we don't need to do that, sorry. We just need to plug all critical points into the second derivative, right? All right, so I have 3 critical points. I have y2 prime at 0. That is 0. Sorry, that is no extrema. That is just inflection point. And then second derivative at -1. You just plug -1 into this, right? You get -60 times -1 cubed plus 30 times -1. And you see that is 30, bigger than 0. So this is local minimum, right? And you plug 1 into the second derivative, you get -60 times 1 cubed plus 60 times 1. Then you get -30, less than 0. So that is your local maximum. You see, that's how we can use the second derivative test to classify local extrema. Of course, you may use the first derivative. Let me show the solutioning here, right? Once you have 3 critical points, you may make the chart for the first derivative. So you may make the following chart: y prime and y, negative infinity, positive infinity, and you have 0 in here, -1 in here, and 1 in here. So you have 4 intervals. Okay, you need to find, just to pick 1 point from each interval and then plug into the first derivative. Then I have, for example, here I pick 2. I plug 2 into this expression because we already have this, right? The sign of the first derivative depends on the sign of -x squared plus 1. So I think, which is easy. But I write 0, 0 in here, so I have negative in here. Between 0 and 1, I have positive. Between -1 and 0, I also have positive. In here, I have negative. So you can see the function is decreasing on negative infinity to -1. The function is increasing, right, to 0, when x approaches 0, and keep increasing, you see, and keep increasing. So, this point is not, extrema, you see that? And then, when x approach 1, the function just change the direction, keep decreasing. So this is your maximum and this is your minimum. Of course, those are local. So you might compare 2 solutions in here. Sometimes you might choose the first derivative test. Sometimes you might choose the second derivative test. So that is your choice. But in my opinion, sometimes the first derivative is good. Because if you have a complicated function, you don't need to find the second derivative, because sometimes that causes, that causes some difficulty, right? Because this function is easy. So you differentiate, okay, that's fine. So we just play with numbers in here in the first derivative. But if your function is good and you can find second derivative easily, so we may use this. All right, so I think we finished our video in here. If you have any questions, just feel free to let me know. Bye.